Sadly, not every limit is going to exist. We've talked about getting some intuition about how limits behave, but it's not always true that it's just going to fall and hit some number on the head. What you might find is really one of three cases. There are others, but these are really the three that you'll see the most often. Is that a limit will just shoot up to infinity or shoot down to negative infinity. Basically just goes and goes and goes, and there's nothing you can do. It doesn't have a limit there. Think about when you were graphing things in pre-cal and had you had asymptotes and the graphs would do like this. Those limits as they go, they shoot off. They don't go anywhere. So those limits don't exist. The second thing you'll find when limits don't exist are that they go to different numbers. So think like piecewise functions where you have like it comes up to a value and then there's a value up here. There's that jump. Well, your limit as you come from the left and your limit as you come from the right end up going towards different numbers. So that limit doesn't exist. The left-hand limit exists and the right-hand limit exists, but they don't agree. So that the limit fails to exist. The third one, and this doesn't really happen until we get to a special type of limit that we'll cover as we go down the line a little bit, and that's when the value sort of oscillates. So think if we were taking x and we were just running wild with it. We were just going, all the way out there, and it just was ding, 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 and it just never was converging to a value. It just kept oscillating. And a thing like a sine wave, right? If you do that, the limit, it doesn't shoot off to infinity or anything, but it never really settles down, maybe is the right term, so it never converges to a single value. So that limit also fails to exist. And you can have that kind of behavior even like as it goes from like 1 to 0, but you have to construct some rather complicated functions that are beyond the scope of what we want to deal with right now. So generally we say that f has no limit, or the limit fails to exist as x approaches a. So I'm going to use this shorthand instead of saying or writing x approaches a to get us used to that. If there's no finite value L for which the limit is x approaches a of f of x equals L. So basically if you can't say this for some finite number L, then the limit doesn't exist. So let's take a look at an example where that's true. Absolute value of x divided by x. Now, you may not remember what the formal definition of the absolute value is, but it's here. You probably know it here, but you don't really know what it is. You may not know what it is on paper. And the idea is that if x is greater than or equal to 0, it's just whatever x is. But if x is less than 0, if x is negative, then it's the negative of what's in there. So that makes sense, right? If it's negative, you negate that to get a positive number. If it's a positive number, you don't have to negate that. You don't have to do anything. Why does that matter? Well, it matters because in the case where x is greater than 0, now we're not going to consider the case where x equals 0 because that's not defined there because we're dividing by it. But in the case where x is greater than 0, the top and the bottom are just x, right? The top is x, the bottom is x, so that's 1. So no matter what x is, that line is equal to 1. Now, in the case where x is less than 0, well then the absolute value is negative x over x, so that's negative 1. So if you were to graph this, if you were going to some graphing utility and graph that, this is the graph you'd get. You'd get a straight line and then just a step and another straight line. So is a kind of a step function there. So what we find is if we were going to do the limit, right, if we were going to say x and f of x, we could say, negative 0.1, negative 0.001, negative 0.00000001, and similarly 0.00001, do another one, 0.001, 0.1. All those numbers there. Well, in all the negative cases, it's -1, -1, -1, 1, 1, 1. And it doesn't matter how small you make those values on either side. It's always -1 here, and it's always +1 there. They're not getting any closer. They never get any closer. Those values don't converge. So you don't have a limit. That's generally the easiest way to see that, is if it's just this constant value here, or if it's constant value there. But you'll see, you know, if you have something like that, your limit doesn't exist because the limit here just rides in clean. The limit here rides in clean, but there's a gap between them. So a lot of times just filling that out, showing that it can't equal it. This is enough to prove. This would be pretty much enough to prove that no matter what you do, it's always going to fail.